Good day everyone. Today we're going to discuss about the cratered worlds. So first, I'm going to ask, what do you understand about the cratered worlds? And do you remember the name of the first American astronaut who first set foot in the moon in July 20, 1969? And do you have any idea about hypothesis of the formation of the moon? And do you think there are similarities of the planet Mercury to the moon? You can share your answer, your ideas through our chat box or virtual participation. Our first topic is about the general properties of the moon. The moon has only 1/80th the mass of Earth and about 1/6 Earth's surface gravity, so low to retain an atmosphere. Moving molecules of a gas can escape from a planet just the way a rocket does. And the lower the gravity, the easier it is for the gas to leak away into space. So while the moon can acquire a temporary atmosphere from impacting comets, this atmosphere is quickly lost by freezing onto the surface or by escape to surrounding space. The moon today is dramatically deficient in a wide range of volatiles, those elements and compounds that evaporate at relatively low temperatures. Some of the moon's properties are summarized in Table 9.1 along with comparative values for Mercury. Exploration of the moon. Most of what we know about the moon today derives from the US Apollo program, which sent 9 piloted spacecraft to our satellite between 1968 and 1972, landing 12 astronauts on its surface. Before the era of spacecraft studies, astronomers had mapped the side of the moon that faces Earth with telescope resolution of about 1 kilometer, but lunar geology hardly existed as a scientific subject. All that changed beginning in the early 1960s. Initially, Russia took the lead in lunar exploration with Lunar Day, which returned the first photos of the lunar far side in 1959, and then with Luna 9, which landed on the surface in 1966 and transmitted pictures and other data to the Earth. However, these efforts were overshadowed in July 20, 1969, when the first American astronaut set foot on the moon. Table 9.2 summarizes the 9 Apollo flights, 6 that landed and 3 others that circled the moon but did not land. The initial landings were on flat plains selected for safety reasons, but with increasing experience and confidence, NASA targeted the last 3 missions to more geologically interesting locales. The level of scientific exploration also increased with each mission, as the astronauts spent longer times on the moon and carried more elaborate equipment. Finally, on the last Apollo landing, NASA included one scientist, geologist, Jack Smith, among the astronauts, as you can see at the figure 9.3. In addition to landing in the lunar surface and studying it at close range, the Apollo missions accomplished 3 objectives of major importance for lunar science. First, the astronauts collected nearly 400 kilograms of samples for detailed laboratory analysis on Earth. These samples have revealed as much about the moon and its history as all other lunar studies combined. Second, each Apollo landing after the first one deployed an Apollo Lunar Surface Experiment Package or the ALSEP, which continued to operate for years after the astronauts departed. And third, the orbiting Apollo command modules carried a wide range of instruments to photograph and analyze the lunar surface from above. The last human left the moon in December 1972, just a little more than 3 years after Neil Armstrong took his giant leap for mankind. The program of lunar exploration was cut off mid-stride due to political and economic pressures. It had just cost about 100 per American spread over 10 years, the equivalent of one large pizza per person per year. Yet for many people, the moon landings were one of the central events in 20th century history. The giant Apollo rockets built to travel to the moon were left to rust on the lawns of NASA, centered in Florida, Texas, and Alabama, although recently some have at least been moved indoors to museums. And today, neither NASA nor Russia have plans to send astronauts to the moon, and China appears to be the nation most likely to attempt this feat. However, scientific interest to the moon is stronger than ever, and more than half a dozen scientific spacecraft sent from NASA, ESA, Japan, India, and China have orbited or landed on our nearest neighbor during the past 2 decades. China has been especially active with the landing on the far side in a sample return, and they have expressed interest in eventually sending Chinese taikonauts to the moon. Lunar exploration has become an international enterprise with many robotic spacecraft focusing on lunar science. The USSR sent a number in the 1960s, including robot sample returns, and recently, China has been active, with 3 landers in a sample return mission. In the Table 9.3 list of are the list of some of the most recent lunar missions. Composition and structure of the moon. The composition of the moon is not the same as that of Earth. With an average density of only 3.3 grams per centimeter cubic, the moon must be made almost entirely of silicate rock. Compared to Earth, it is depleted in iron and other metals. It is as if the moon were composed of the same silicates as Earth's mantle and crust, with the metals and the volatiles selectively removed. These differences in composition between Earth and Moon provide important clues about the origin of the Moon, a topic that we will cover in detail later in this chapter. Studies of the Moon's interior, carried out with seismometers taken to the Moon as part of the Apollo program, confirmed the absence of a large metal core. The Twin Gill spacecraft launched into lunar orbit in 2011 provided even more precise tracking of the interior structure. We also know from the study of lunar samples that water and other volatiles have been depleted from the lunar crust. The tiny amounts of water detected in the samples were originally attributed to small leaks in the container cell that admitted water vapor from Earth's atmosphere. However, scientists have now concluded that some chemically bound water is present in the lunar rocks. Most dramatically, water ice has been detected in permanently shadowed craters near the lunar poles. In 2009, NASA crashed a small spacecraft called the Lunar Crater Observation and Sensing Satellite, or the LCROSS, into the crater caboose near the moon's south pole. The impact at 9,000 kilometers per hour released energy equivalent to 2 tons of dynamite, blasting a plume of water vapor and other chemicals high above the surface. This plume was visible to telescopes in orbit around the moon, and the LCROSS spacecraft itself made measurement as it flew through the plume. A NASA spacecraft called the Lunar Reconnaissance Orbiter also measured the very low temperatures inside several lunar craters, and its sensitive cameras were even able to image crater interiors by starlight. The total quantity of water ice in the moon's polar craters is estimated to be hundreds of billions of tons. As liquid, this would only be enough water to fill a lake 100 miles across, but compared with the rest of the dry lunar crust, so much water is remarkable. Presumably, this polar water was carried to the moon by comets and asteroids that hit its surface. Some small fraction of the water froze in a few extremely cold regions, or the cold traps, where the sun never shines, such as the bottom of water craters at the moon's poles. One reason this discovery could be important is that it raises the possibility of future human habitation near the lunar poles or even of a lunar base as a way station en routes to Mars and the rest of the solar system. If the ice could be mined, it would yield both water and oxygen for human support, and it could be broken down into hydrogen and oxygen, a potent rocket fuel. Second topic, the lunar surface. General appearance. So if you look at the moon through the telescope, you can see that it is covered by impact craters of all sizes. The most conspicuous of the moon's surface features those that can be seen with the unaided eye and that make up the feature often called the man in the moon, are vast splotches of dark lava flows. Centuries ago, the early lunar observers thought that the moon had continents and oceans and that it was possible abode life. They called the dark areas seas Maria in Latin or Marie in the singular, pronounced Marie. Their names, Mare Nubium or the Sea of Clouds, Mare Tranquillitatis or the Sea of Tranquility, and so on, are still in use today. In contrast, the land areas between the seas are not named. Thousands of individual craters have been named, however, mostly for great scientists and philosophers, at a figure 9.6. Among the most prominent craters are those named for Plato, Copernicus, Tycho, and Kepler. Only has a small crater, however, reflecting his low standing among the Vatican scientists who made some of the first lunar maps. We know today that the resemblance of lunar to terrestrial ones is superficial. Even when they look somewhat similar, the origins of lunar surface features such as craters and mountains are very different from their terrestrial counterparts. The moon's relative lack of together with the absence of air and water make most of its geological history unlike anything we know on Earth. Lunar history. To trace the dated history of the moon or of any planet, we must be able to estimate the ages of individual rocks. Once lunar samples were brought back by the Apollo astronauts, the radioactive dating techniques that had been developed for Earth were applied to them. The solidification ages of the samples range from about 3.3 to 4.4 billion years old, substantially older than the most of the rocks on Earth. For comparison, as we saw in the chapter on Earth, moon and sky, both Earth and the moon were formed between 4.5 and 4.6 billion years ago. Most of the crust of the moon is about 83% consists of silicate rocks called anorthosites. These regions are known as the Lunar Highlands. They are made of relatively low density rock that solidified on the cooling moon like slag floating in the top of a smelter. Because they formed so early in lunar history, for between 4.1 and 4.4 billion years ago, the highlands are also extremely heavily cratered, bearing the scars of all those billions of years of impacts by interplanetary debris. Unlike the mountains on Earth, the moon's highlands do not have any sharp folds in their ranges. The highlands have low, rounded profiles that resemble the oldest, most eroded mountains on Earth. And because there is no atmosphere or water in the moon, there has been no wind, water, or ice to curve them into cliffs and sharp peaks, the way we have seen them on shape in Earth. Their smooth features are attributed to gradual erosion, mostly due to impact crater from meteorites. The Maria are much less cratered than the highlands and cover just 17% of the lunar surface, mostly on the side of the moon that faces Earth, as you can see at the figure 9.9. Today, we know that the Maria consists mostly of dark-colored basalt or the volcanic lava laid down in the volcanic eruptions billions of years ago. Eventually, these lava flows partly filled in the huge depressions called impact basins, which had been produced by collisions of large chunks of material with the moon relatively early in its history. The basalt on the moon, at the figure 9.10, is very similar in composition to the crust under the oceans of Earth or the lavas erupted by many terrestrial volcanoes. The youngest of the lunar impact basins is Marie Orientale, shown in figure 9.11. Volcanic activity may have begun very early in the moon's history, although most evidence of the first half-billion years is lost. What we do know is that the major marivolcanism, which involved the release of lava from hundreds of kilometers below the surface, ended about 3.3 billion years ago. After that, the moon's interior cold and volcanic activity was limited to a very few small areas. The primary forces altering the surface come from the outside, not the interior. On the lunar surface, the surface is fine and powdery. I can pick it up closely with my tooth, but I can see the footprints of my boots in the trees and the fine sandy particles. According to Neil Armstrong, from Apollo 11 astronaut, immediately after stepping into the moon for the first time. And the surface of the moon is buried under a fine-grained soil of tiny, shattered rock fragments. The dark basaltic dust of the lunar Maria was kicked up by every astronaut footstep, and thus eventually worked its way into all of the astronauts' equipment. The upper layers of the surface are porous, consisting of loosely packed dust into which their boots sank several centimeters at the figure 9.12. This lunar dust, like so much else on the moon, is the product of impacts. Each cratering event, large or small, breaks up the rock of the lunar surface and scatters the fragments. Ultimately, billions of years of impacts have reduced much of the surface layer to particles about the size of dust or sand. In the absence of any air, the lunar surface experiences much greater temperature extremes than the surface of Earth. Even though Earth is virtually the same distance from the Sun, near the local noon when the Sun is highest in the sky, the temperature of the dark lunar soils rises above the boiling point of water. And during the long lunar night, which like the lunar day lasts 2 Earth weeks, the temperature drops about 173 degrees Celsius. The extreme cooling is a result not only of the absence of the air, but also of the porous nature of the most dusty soil, which cools more rapidly than solid rock would. So, our third topic is about the impact craters. Volcanic versus impact origin of craters. The moon provides an important benchmark for understanding in the history of our planetary system. Most solid worlds show the effects of impacts, often extending back to the era when a great deal of debris from our system's formation process was still present. On Earth, this long great deal history has been erased by our active geology. On the moon, in contrast, most of the impact history is preserved. If we can understand what has happened on the moon, we may be able to apply this knowledge to other worlds. So the moon is especially interesting because it is not just any moon but our moon, a nearby world that has shared the history of Earth for more than 4 billion years ago and preserve a record that for Earth has been destroyed by our active geology. Until the middle of the 20th century, scientists did not generally recognize that lunar craters were the result of impacts. Since impact craters are extremely rare on Earth, geologists did not expect them to be the major feature of lunar geology. They reasoned perhaps a unconsciously that since the craters we have on Earth are volcanic, the lunar crater must have a similar origin. One of the first geologists to propose that lunar craters were the result of impacts were Grove Kelbert, a scientist with the U.S. Geological Survey in the 1890s. He pointed out that the large lunar craters, the mountain rim, circular features with floors generally below the level of the surrounding plains, are larger and have different shape from known volcanic craters on Earth. Terrestrial volcanic craters are similar and deeper and almost always occur at the tops of volcanic mountains. At the pictures you can see at the figure 9.13. The only alternative to explain the moon's crater was an impact origin. His careful reasoning, although not accepted at the time, laid the foundations for the modern science of lunar geology. Gilbert concluded that the lunar craters were produced by impacts, but he didn't understand why all of them were circular and not oval. The reason lies in the escape velocity, the minimum speed that a body must reach to permanently break away from the gravity of another body. It is also the minimum speed that a projectile approaching Earth or the Moon will hit with. Attracted by the gravity of the larger body, the incoming chunk strikes with at least escape velocity, which is 11 kilometers per second for Earth and 2.4 kilometers per second or 5,400 miles per hour for the Moon. To the escape velocity is added whatever speed projectile is already had with respect to Earth or Moon, typically 10 kilometers per second or more. At these speeds, the energy of impact produces a violent explosion that excavates a large volume of material in a symmetrical way. Photographs of bomb and shell craters on Earth confirm that explosion craters are always essentially circular. Only following World War I did scientists recognize the similarity between impact craters and explosion craters, but sadly Gilbert did not live to see his impact hypothesis widely accepted. The cratering process. Let's consider how an impact at these high speeds produces a crater. When such a fast projectile strikes a planet, it penetrates 2 or 3 times its own diameter before stopping. During these few seconds, its energy of motion is transferred into a shock wave which spreads through the target body and into heat which vaporizes most of the projectile and some of the surrounding target. The shock wave fractures the rock of the target while the expanding silicate vapor generates an explosion similar to that of a nuclear bomb detonated at ground level, as you can see at the figure 9.14. The size of the excavated crater depends primarily on the speed of impact, but generally it is 10 to 15 minutes the diameter of the projectile. An impact explosion of the sort described above leads to a characteristic kind of crater as shown in figure 9.15. The central cavity is initially bowl-shaped. The word crater comes from the Greek word for bowl, but the rebound of the crust partially fills it in, producing a flat floor and sometimes creating a central peak. Around the rim, landslide create a series of terraces. The rim of the crater is turned up by the force of the explosion, so it rises above both the floor and the adjacent terrain. Surrounding the rim is an ejecta blanket consisting of material thrown out by the explosion. This debris falls back to create a rough, hilly region typically about as wide as the crater diameter. Additional, higher speed ejecta fall of greater distances from the crater, often digging small secondary craters where they strike the surface, as shown in the figure 9.9. Some of these streams of ejecta can extend for hundreds or even thousands of kilometers from the crater, creating the bright crater rays that are prominent in lunar photos taken near full phase. The brightest lunar crater rays are associated with large young craters such as Kepler and Tycho. Observing the Moon. The Moon is one of the most beautiful sights in the sky, and it is the only object close enough to reveal its topography without a visit from a spacecraft. A fairly small amateur telescope easily shows craters and mountains on the Moon as small as a few kilometers across. Even as seen through a good pair of binoculars, we can observe that the appearance of the Moon's surface changes dramatically with its phase. At full phase, it shows almost no topographic detail, and you must look closely to see more than a few craters. This is because sunlight illuminates the surface straight on, and in this flat lighting, no shadows are cast. Much more revealing is the view near first or third quarter when sunlight streams in from the side, causing topographic features to cast sharp shadows. It is almost always more rewarding to study a planetary surface under such oblate lighting with the maximum information about surface relief can be obtained. The flat lighting at full phase does, however, quintate brightness contrast on the Moon such as those between the Maria and Highlands. Notice in figure 9.16 that several of the large Marie craters seem to be surrounded by white material in that the light streaks or rays that can stretch for hundreds of kilometers across the surface are clearly visible. These lighter features are ejecta, splash out from the crater forming impact. By the way, there's no danger in looking at the Moon with binoculars or telescopes. The reflected sunlight is never bright enough to harm your eyes. In fact, the sunlit surface of the Moon has about the same brightness as a sunlit landscape of dark rock on Earth. Although the Moon looks bright in the night sky, its surface is on average much less reflected than Earth's with its atmosphere and white clouds. This difference is nicely illustrated by the photo of the Moon passing in front of Earth taken from the Deep Space Climate Observatory spacecraft as shown in figure 9.17. Since the spacecraft took the image from a position inside the orbit of Earth, we see both objects fully illuminated, which is the full Moon in full Earth. And by the way, you cannot see much detail on the Moon because the exposure has been set to give a bright image of Earth, not the Moon. One interesting thing about the Moon that you can see without binoculars or telescopes is popularly called the new Moon in the old Moon's arms. Look at the Moon when it is a thin crescent, and you can often make out the faint circle of the entire lunar disk. Even though the sunlight shines on only the crescent, the rest of the disk is illuminated not by sunlight but by the Earth light, sunlight reflected from Earth. The light of the full Earth on the Moon is about 50 times brighter than that of the full Moon shining on Earth. For the Moon, these calculations indicate that a crater 1 kilometer in diameter should be produced about every 200,000 years, a 10 kilometer crater every few million years, and 1 or 2 100 kilometer craters every billion years. If the cratering rate has stayed the same, we can figure out like long it must have taken to make all the craters we see in the lunar Maria. Our calculations show that it would have taken several billion years, and this result is similar to the age determined for the Maria for dating of returned samples 3.3 to 3.8 billion years old. The fact that these two calculations agree suggests that astronomers' original assumption was right. Comets and asteroids in approximately their current numbers have been impacting planetary surface for billions of years. Calculations carried out for other planets and their moons indicate that they also have been subject to about the same number of interplanetary impacts during this time. We have good reason to believe, however, that earlier than 3.8 billion years ago, the impact rates must have been a great deal higher. This becomes immediately evident when comparing the numbers of craters on the Lunar Highlands with those on the Maria. Typically, there are 10 times more craters on the Highlands than on a similar area of Maria. Yet, the radioactive dating of Highland samples show that they are only a little older than the Maria, typically 4.2 billion years rather than 3.8 billion years. And if the rate of impacts had been constant throughout the moon's history, the Highlands would have had to be at least 10 times older. They would thus have had to form 38 billion years ago, long before the universe itself began. In science, when an assumption leads to an implausible conclusion, we must go back and re-examine that assumption. In this case, the constant impact rate. The contradiction is resolved if the impact rate varied over time with a much heavier bombardment earlier than 3.8 billion years ago at the figure 9.19, and this heavy bombardment produced most of the craters we see today in the Highlands. We have been exploring that large impacts, especially during the early history of the solar system, played a major role in shaping the worlds we see, is not unique to our study of the moon. As you read through the other chapters about the planets, you will see further indications that a number of the present-day characteristics of our system may be due to its violent